we are still in falling film example, but for this one is the diffusion of gas or oxygen gas in liquid phase, limiting the overall reaction. Alright, an aqueous solution containing 10 ppm by weight of an organic contaminant of molecular weight 120. So given in the question is, let's say the organic contaminant A, okay, at initial the concentration is 10 ppm with a molecular weight of molecular weight of A is 120 gram per mole. Is to be removed by air oxidation. So, the reaction of organic contaminant A with oxygen in a 1 centimeter diameter falling film reactor. So, you can draw the falling film reactor. Okay, so this is your falling film reactor. And then form a film. So the film with 1 mm thick. So the thickness of the film is 1 mm. So 1 mm thickness 1 mm or equal to 0.1 cm. Okay, equal to 0.1 cm thickness for both liquid film. Okay, then the reaction occur at 25 degrees C. The liquid flows at average velocity 10 cm per second. So average velocity U L 10 cm per second, while the air at 1 atmosphere flows at average velocity 2 cm per second. So not all the properties or all the values given in the question that we are going to use to solve the problem. So you don't be confused with all the value given in the question. If it is not related, just ignore the value. So for gas, velocity is 2 cm per second. The reaction in the liquid phase has stoichiometric of A plus 2O2 to produce product P with a rate, okay, so given R, rate of reaction in liquid phase is KL CAL CO2L. Alright. Now the question is, estimate the reactor length needed to reduce the organic concentration to 1 ppm. Okay, now what you need to do is to calculate the length of reactor L. So what is the value of L? Okay, then given the organic concentration reduced to 1 ppm. So at initial Ca0 10 ppm, therefore Ca, remaining A is 1 ppm. So Ca0. So you can calculate the conversion if required in the question in order for you to solve the problem. If not, you just can use this value. Okay, and then okay, if the reaction actually occur on a catalyst on the wall, right? So we need to jot down here the important information. Reaction on the catalyst on the wall consists of catalyst. So this is the most important information. Assume that the reaction rate on the wall is infinite and the process is limited by diffusion of oxygen. So on the wall, so this is the wall of catalyst, that the wall of reactor that contain catalyst. So this is the catalyst on the wall of reactor. Right? Okay. So the reaction will occur here. Okay, on the wall of catalyst. Catalyst that attached to the wall, and the reaction occur on the surface of catalyst. Okay, itu maksudnya. But the reaction is limited by diffusion of oxygen through the liquid. So meaning that the oxygen in liquid phase, the diffusion of oxygen in liquid phase to the wall ataupun to the surface of catalyst. So transfer the mass transfer of oxygen in liquid phase to the external surface of catalyst, limiting the reaction. That's the meaning of the question here. Maksud that we need to assume that the process is limited by diffusion of oxygen through the liquid. Okay, so mass transfer of oxygen in liquid phase limiting the reaction because the reaction occur on the surface of catalyst. So mass transfer of oxygen to the surface of catalyst limiting the reaction. Right. Okay. Now, given the diffusivity of oxygen in liquid phase given as 10⁻5 centimeter square per second, and the concentration profile is linear. Henry's law constant for oxygen in water is 1 times 10 power of 5 atmosphere. So when the Henry's law constant given, meaning that you need to calculate the concentration of oxygen in liquid phase. Alright, first step, we need to write the mass balance equation. Alright, the falling film reactor can be modeled as a PFR. Therefore, the mass balance, you can write the mass balance equation for PFR. And the reaction occur in liquid phase. Velocity of liquid phase, U dCAL per dz equal to, so when mass transfer limiting the reaction, therefore the rate of reaction can be negligible. So your overall mass balance becomes negative A over V because mass transfer of mass transfer of oxygen liquid to the external surface of catalyst. And we divide it with 2 because based on stoichiometry. So remember again from previous example, as I told you, negative RA per A equal to negative RB per B. The rate reaction is 4A, but now we consider the mass transfer of oxygen. So we need to divide it with the stoichiometry of oxygen, which is 2. So negative A per 2V, or you can write it as so biarkan A over negative 2. Okay, saya padam yang 2 here. Okay. So you can write it as A over V. V tak macam V pula. A over V, Km, okay, mass transfer, Km, C, concentration of oxygen in bulk fluid is in liquid phase, to the external surface of catalyst, concentration of oxygen to the external surface, and then we divide it with 2. Okay, so this is the mass balance equation. Right, so concentration of oxygen in bulk fluid actually in liquid phase. Concentration of oxygen at the external surface of catalyst also in liquid phase. Okay, but we can consider or assume that the concentration of oxygen, the concentration gradient of oxygen to the surface of catalyst can be negligible, right? Therefore, we can simplify the equation as U L dCal per dz equal to negative A over V Km over 2. Okay, multiply with the concentration of oxygen in bulk fluid. So, because the concentration gradient can be negligible. Maksudnya, the change of concentration at the surface of catalyst to not much. That's why it can be negligible. Right. So, this is your overall mass balance equation. Okay. So, now we look at into one by one the term. Okay, for each term, especially A over V. Okay, concentration, saya tunjuk yang paling senang. Concentration of oxygen in liquid phase. This one you can calculate it from Henry's law constant. Okay, so oxygen in liquid phase, PO2 equal to, okay, partial pressure of oxygen in gas phase equal to Henry's law constant multiply with the fraction of oxygen in liquid phase. So when you have the fraction of oxygen in liquid phase, so you can calculate the concentration. So, okay, calculate XO2 value, okay, from this equation. Okay, next step is calculate the concentration of oxygen in liquid phase equal to XO2 multiply with the density of water, and because in the question stated that oxygen is in water, so divide with molecular weight of water. Then you will get the concentration of oxygen in liquid phase. So this value is the value of CO2 in liquid phase in the bulk fluid. Okay, next, A over V. Okay, for A over V, in this case, because the reaction occur on the surface of catalyst at the wall, therefore, A over V is 4 D naught. Okay, divide with D naught square minus DI square. Okay, because the reaction occurred not on the liquid film but on the surface of catalyst on the wall. That's why D naught here, not DI. So yang based on previous example, the reaction occur in liquid film. Okay, so that's why we use for DI, inner diameter. But for reaction on the wall of reactor, so the diameter here is D outer. So that's the difference between the reaction in liquid phase and reaction on the surface of catalyst. So refer back to the previous example of falling film. Okay. Then insert all this equation into the mass balance equation to solve the integration. Alright, so the mass balance equation becomes UL dCAL per dz. So A over V tadi so negative sign. Oh, itulah negative. A over V equal to 4 D naught per D naught square minus DI square. Okay, in bracket. Supaya you tak confuse later. Km over 2 CO2 in liquid phase. So Km, saya lupa to calculate Km. Okay, Km not given in the question, but the reaction occur in cylinder. So we can calculate the Km value. Okay, and diffusivity also given. So Km equal to SH DO2 per D. Okay, this D not the outer diameter or not the inner diameter, but the diameter where the reaction ataupun where the mass transfer occur. Alright, so okay, I draw the reactor again. Okay, so reactor consists of catalyst, then falling film. Okay, thickness, we know that thickness is 0.1 cm. So remember, in Sherwood number or mass transfer coefficient equation, D here is characteristic diameter. Okay, so this D is characteristic diameter. Characteristic diameter. Okay, so therefore, the characteristic diameter where the reaction occur is actually equal to the thickness of the film. See? So in this case, it's equal to the thickness of the film. Okay, thickness of film, which is 0.1 centimeter. Right, the diameter of reactor D naught from wall to wall, and the outer inner diameter is this value, the gap between the film. So this is DI. So when you want to insert the value, D naught, DI, and D. So D untuk mass transfer coefficient for this case is thickness of film. Okay, diffusivity of oxygen given Sherwood number for laminar flow in cylinder is 8/3. So Sherwood number 8/3. So diffusivity as given, and the characteristic diameter is actually equal to the thickness of film, which is 0.1 centimeter. Okay. So for the reaction, liquid phase reaction on the surface of catalyst is actually quite complicated compared to another 3 cases that we have learned in previous falling film example. Okay, then we can rearrange the equation. So CO2 in liquid phase dan Km dan the value of diameter dan what else? So just rearrange the equation because we want to calculate the length of reactor. So length of reactor is refer to integration of position where the reaction occur, dz. So rearrange dz, so duration from 0 to L, okay, position of 0 to L equal to, so we need to rearrange for the concentration, so UL, so negative sign later, UL times 2, right, because we divide with 2, so and then times D naught square minus DI square, right, divide with 4 D naught Km, CO, concentration of oxygen in liquid phase. Then baru kita consider the negative sign because we want to integrate for Ca. Okay, bracket negative dCA, integrate from Ca0 to Ca. Okay, so just solve this integration and you will get the length of reactor. So unit, it can be centimeter or you can change it to meter later.